Hello and welcome to the Al-Attiyah Foundation podcast. My name is Stephen Cole. Today, I'm delighted to welcome someone who can be accurately described as the doyen of the energy transition, Frank Wouters, a distinguished energy leader with over 30 years in renewable energy. Frank is renowned for spearheading initiatives around the world, from small-scale PV solar electrification in Uganda to strategic investments in groundbreaking projects like the London Array and Shams concentrated solar plant. Among a number of other roles, Mr. Wouters is chairman of the MENA Hydrogen Alliance. Today, though, we're going to be talking about the future of renewable energy and the gas pyrolysis process for producing hydrogen. So, Frank, welcome to the podcast.
Thanks, Stephen. It's a pleasure to be here.
Well, let's start, Frank, with explaining our terms. What is the fundamental process of methane pyrolysis, and how does it differ from traditional hydrogen production methods like steam methane reforming?
Well, pyrolysis is a thermochemical reaction that basically breaks down methane, which is CH4, into its constituent elements, hydrogen and solid carbon. And that happens at high temperatures and without oxygen. That's important because if you then compare it to, let's say, the most widely used way to produce hydrogen through steam methane reforming, that involves steam. And steam is water, so that has oxygen as part of it. And then when you crack the methane, you also crack the water, and then the carbon has a tendency to recombine with oxygen, and then you have CO2. So the fundamental difference is that pyrolysis produces hydrogen and solid carbon, whereby steam methane reforming produces hydrogen and CO2. So pyrolysis is by nature cleaner.
Well, that's always to be welcomed, isn't it? The cleaner energy. There are various ways to carry out gas pyrolysis. What are the differences between thermal pyrolysis, catalytic pyrolysis, plasma pyrolysis, and molten media pyrolysis?
Yes, thank you. So methane pyrolysis is fundamentally a so-called endothermic process, which means that it requires heat to happen. And high temperature heat drives the decomposition reaction. And typically, if you don't use a catalyst, I'll get back to that later, you need temperatures above 1200 degrees Celsius, even up to 1400. And then, you have, let's say, the environmental conditions to crack the methane. Now, if you add a catalyst, that actually reduces the required temperatures and is hence more energy and cost efficient. And people have been studying and working on a range of catalyst materials. And nickel-based catalysts are among the most common and extensively studied because they demonstrate good activity at moderate temperatures. Now, one of the drawbacks of these catalysts is that you always have some element of carbon deposits, what we like to call coking. And that is a problem that you need to somehow manage. Some supported metal catalysts, where catalytically active metals such as nickel, cobalt, or iron are deposited onto high surface area support materials like alumina, silica, or zeolite. They offer improved stability and selectivity. So basically, you take a carrier material that has a three-dimensional structure with a large surface area, and then you put that small layer of catalytically active metal on it. There is also a small group of very expensive noble metal catalysts, including platinum and palladium. So they further reduce the temperature, so they're more energy efficient, but come at a high cost. So it's probably more a niche application rather than larger scale. And then you can have catalysts that consist of, let's say, a combination of metals. So you have nickel and cobalt, for example, that you can use together. And the last group of catalysts would include perovskite types, and they're also being studied. Now, how to get the temperature to, let's say, the methane. One of the most widely used systems is using a plasma, which is an ionized gas that is composed of highly energized particles. And that high temperature heat in the plasma, cracks cracks the methane. The temperatures are extremely high, so they can go up to 10,000 Kelvin, and then you don't need any catalyst. So you don't have all the issues associated with catalytic materials, as I mentioned before, the coking, etc. So you don't have that with plasma. Another method to get temperature into the methane is microwaves. This is actually something that a British company is championing called Levidian. They have a joint venture here in Abu Dhabi with ADNOC, and they're producing hydrogen and carbon. A last method to produce or to use pyrolysis is a liquid metal medium. So the advantage of that is you basically feed the methane gas through a bath of molten metal, that you don't have this coking problem. So you don't have carbon depositions on the catalyst because it doesn't dissolve in molten metal. So it's easy to separate. And that's it. Those are the types that are currently being used.
Wow. Well, you've laid out very clearly the processes. Which ones do you think would be commercially viable?
Well, there is already a few, and the plasma technology championed by a company called Monolith, currently operating in Nebraska. They use plasma, and they've been doing that for 10 years. But a lot of the others that I just mentioned, it's probably too early to tell, to be honest. Many are still in early stages, are highly promising, but they need to go through a number of development stages before you can really tell whether this is commercially attractive or not.
Okay, so we're talking very early days. What is the state of development of this process now? Are there any industrial scale or pilot plants in operation?
Yes, there are. As I mentioned, Monolith in Nebraska. It was founded in 2012, and they built their plant, which is commercial, in 2015. And they have had industrial backing. So their investors include Mitsubishi Heavy Industries from Japan, Nextera Energy, and SK from South Korea. So their Olive Creek 1 facility has been producing carbon black and hydrogen for 10 years now. And the main application for the carbon black, and this is actually the origin of the company, is they were not interested in the hydrogen, but they were interested in the carbon. So the carbon black actually goes to car tires and other applications where you use carbon black. Now, when hydrogen became interesting, that's actually when SK joined the company, and they are now planning to make an ammonia facility using the hydrogen that is produced at the Olive Creek facility. So that is, a commercial plant that has been operational for 10 years. But there is others in Ludwigshafen in Germany. BASF, the large chemical giant from Germany, has been studying methane pyrolysis since 2010, and they've been operating a prototype of their moving bed reactor already for the last 5 years.
So as the research goes on and as the development goes on, probably the logic would be that they will find more and more applications.
Yes, absolutely. I mean, this is something, if you have, let's say, the feedstock, if you have methane, then this is certainly very interesting to look at.
Okay. So what are the key technical challenges in scaling up gas pyrolysis for industrial use, particularly regarding reactor design and carbon handling?
Well, the main challenges, they relate, to those two things. One is the high temperature. So anything that goes beyond 1,000 degrees Celsius is challenging for many reasons, but also carbon formation. So the materials of the construction, but also the presence of carbon and potentially corrosive molten catalyst complicate that material selection. So the reactors that you build need to withstand those conditions without degradation or failure. Carbon management is something. I mean, you do have carbon deposits on the inside of the reactor, so you can have reactor fouling that can reduce efficiency and potentially causing operational issues. So effective strategies for carbon removal or in situ management are crucial. how you design your reactor and optimize it, is a challenge in the sense that you have various design options. You can do a fixed bed, a fluidized bed, molten metal reactors. They've all been explored, and each design has its own sets of advantages, but also challenges that relate to heat transfer, mass transfer, byproduct separation. How do you get the carbon out, etc.? So optimizing that geometry and flow patterns is essential, and people are working on all of these things. The byproduct removal, as I said before, how do you get the carbon out depends on the type of system that you're using and how to do that. Mechanical removal systems in gaseous forms, etc. That's important. And then, last but certainly not least, if you have a catalyst, how do you prevent or reduce the effect of coking? So the deposition of carbon on the catalyst material, and how do you regenerate your catalyst, etc. These are all, the technical challenges that people are working on.
So, as you said, gas pyrolysis produces solid carbon as a byproduct instead of CO2. So what are the potential uses for the carbon, and are they sustainable in the long term?
Yeah, that's a great question, because the type of carbon that you get, and there's various types of carbon, even though it's all the same simple element, it depends on the type of reactor. You can have carbon black, you can have graphite, carbon nanotubes, and carbon nanofibers, and each has their own specific applications. Carbon black, like monolith in Nebraska, is used in rubber tires, but it also serves as a pigment, a UV stabilizer, for example, in plastics. But it's also a conductive or insulating agent in plastics and inks and coatings, and it's because it's conductive, it's also an anti-static agent. And for example, something like an automotive fuel cap, you put carbon black in there because you can't have a spark when you unscrew, your fuel cap, so you don't blow up your car. So those are very practical applications of carbon black. Graphite is a critical raw material for anodes and lithium-ion batteries, but it's also being used in metallurgical coke, carbon fibers, etc., etc. Carbon nanotubes are additives in structural materials. It's very strong. So you add it to electronics, optics, and plastics. But it's also an interesting molecule or set of molecules to basically better administer medicine in pharmacy. So basically what they do is you have a medicine inside the carbon nanotube, and that sort of delays the administration of that drug. So you can use it in cancer therapy.
That's incredible. That's an amazing application, isn't it?
Yes, it is. It is. So people are looking at cancer therapy, gene therapies, tissue regeneration, but also biosensor diagnostics and as antioxidants. So it actually allows you to, not have to go to the doctor every 10 minutes, but the carbon nanotubes does that for you. Carbon nanofibers, lastly, they offer high strength, flexibility, and large specific surface area. Again, also high thermal and electrical conductivity. And they're being used in batteries and supercapacitors, electrode materials, et cetera, et cetera. And lastly, and I think this is an interesting aspect of, let's say, the new carbon economy, if you will. Carbon is also required in soil regeneration. So carbon will be used and will be required to do soil improvement. So that's an agricultural application for which you need large amounts. And this is certainly interesting in the future.
And all good news. So what is the energy balance, Frank, of gas pyrolysis compared to other low carbon hydrogen production routes such as electrolysis or biomass gasification? Because as I understand it, it's an endothermic reaction. So where will the additional heat needed come from?
No, absolutely. I mean, we do need heat. As I said before, you crack methane molecules into its elements, and that requires energy. And the good news is that it's actually compared to other methods much better. So we require about 7 kilowatt hours of energy for 1 kilo of hydrogen. If you compare that to the typical energy use in water splitting in an electrolyzer, that requires 7 times more energy. So it's a very energy efficient way to produce hydrogen. and it's hence then a very cost-effective alternative for CO2-free hydrogen production. And then you can also look at all kinds of waste heat streams whereby you get synergies in industrial processes whereby you further reduce, let's say, the net energy input into the process. So it's very energy efficient.
How pure then is the hydrogen produced through gas pyrolysis, and what additional steps are needed to meet industrial standards?
Yeah, that's a good question, because the reality is that gas pyrolysis still often contains components that need removal. And for example, if you then would like to use the hydrogen in a fuel cell, which is a very sensitive device, you do need gas separation and purification to take the gas purity levels up to 99.99% or higher. But at the same time, gas purification and separation is industrial practice. It's not very complicated. It's also not super expensive, but we do need that.
Everybody's measuring our carbon footprints, aren't they? So how do you assess the overall carbon footprint of gas pyrolysis across the full value chain from feedstock to carbon management?
Yeah, it's relatively good in the sense that it has a low carbon intensity of, let's say, roughly half to 1 kilo of CO2 emission equivalent per kilo of produced hydrogen. And that largely depends on the source of natural gas. Now, if you're really adventurous, and this is an exciting option, you can also make renewable natural gas. So it doesn't have to be fossil. So you can make natural gas from biogenic sources, and then you actually have a negative carbon footprint. And then some even like to call this super green hydrogen. And to put it into perspective, so we call this hydrogen turquoise hydrogen. It's better in terms of CO2 in terms of CO2 emissions, better than gray and blue. And if you're using renewable natural gas, it's even better than green hydrogen.
So what will the role be of gas pyrolysis? Will it be used in hard to abate sectors such as steel, cement, and chemicals that all have huge carbon footprints, or in a more general role in just producing hydrogen?
Well, gas pyrolysis has great potential when you have abundant natural gas. I think that's the starting point. And where will you then use the hydrogen? That's a generic question. Where there is a market for hydrogen, which is a wide spectrum of applications ranging from fertilizers, steel, transport, but even bulk energy storage. So that's the answer to that question.
Well, given that the main use of hydrogen at the moment, anyway, is in refineries for desulfurization, how will gas pyrolysis fit into refineries?
Well, that's certainly an interesting application, whereas the reality is that the main drive in refineries currently is to replace the steam methane reforming units by electrolyzers, also supported by European legislation. All the European refineries are currently looking into this, and I haven't seen many gas pyrolysis alternatives to that. But it's certainly an interesting option to consider.
You mentioned turquoise hydrogen. What kind of economic conditions are needed for it to compete with grey or green hydrogen?
Well, first of all, it needs to be available and proven at scale. And I think the reality is that the determining factor is, of course, the price of the feedstock. That's the price of the natural gas. If you compare it to green hydrogen, which is made using renewable electricity and water, 60 to 70% of the price of green hydrogen is determined by the price of green electricity. Whereas for turquoise, the electricity input is much less, so it's more determined by the price of natural gas. Taking all that into account, a recent estimation by Hydrogen Europe told us that turquoise hydrogen is the cheapest clean hydrogen production pathway in Europe today.
That's quite a claim. What infrastructure is needed to support the widespread deployment of pyrolysis plants, especially in terms of feedstock supply and carbon storage or utilization?
Well, the plants require a connection to a natural gas grid. So that is, number one, you have to have the natural gas as an input. And at scale, once you go bigger, you also need probably a hydrogen grid, so a connection to a hydrogen backbone. So those are the two, grids that are required when you go to larger scales. Carbon storage, is much less of an issue. A solid material can be stored relatively straightforward, and the type of carbon then determines how you do that, which is different from carbon black to graphene, for example.
So you're talking scales. How scalable will the gas pyrolysis process be?
Well, the monolith factory, Olive Creek 1 in Nebraska, we've seen the successful scale up of technology. So how that works, and reactors can be made bigger and are by nature modular. There is various different types. Some are continuous, others are batch type, but most pyrolysis processes can be continuous, and scaling is not a real issue. So that's relatively simple to do.
Okay, well, Frank Wouters, that's my last question. And thank you very much for providing your expertise and knowledge on this process. You've made it very clear, and we've certainly learned a lot more about the process of producing hydrogen from natural gas. And thank you to the listeners for tuning in. A new Al-Attiyah Foundation podcast will be released in the next few weeks on our website and social media channels. If you haven't already, follow us on X, formerly Twitter, YouTube, LinkedIn, and now Instagram. But for now, from Frank Wouters and me, Stephen Cole, until the next time, goodbye.